Alright, this is kind of the follow-up to the magnetic force on a current carrying wire, where there's just a steady flow of charges. This is more specific about, okay, what is the magnetic force acting on a single moving charge? Okay, so the very beginning of this, we're gonna derive this particular equation. So I've got an explanation up here. It says if I have a positive charge Q moving with a speed of v to the right. In the time t, the charge will move a length, L, which would be equal to v times delta t. Now this is just, if we go all the way back to kinematics, we could just say, if this is AP, we got delta x is the average velocity times time, or we could say S is v times t in IB. It doesn't matter. The distance you travel, L, the length in this case, is equal to the velocity of that object times the time. That's all self-explanatory. In this, the current created by I, or the current I created by the charge, because we have charge over time, that is current, okay? So we've got I equals Q over T. Then the force on that particular charge is as follows. So, starting off with our F-Bill equation. F equals BIL sine of theta. Now, I kept the sine of theta here. I kept it down here. So, I, if I look back up in my explanation, is Q over delta T. So if I bring Q over delta T in, I can get rid of I. L would be equal to V delta T. So I can put in V delta T for L. So the delta T's go away, and you're left with BQV. Now it's oftentimes rewritten as QVB sine of theta. Okay. Now, in the previous example, it was the angle between the current and the field. Well, what's taken place of the current in this particular situation is the velocity. Now, I always think of them as being pretty much the same thing, because if current is flowing, then that is also the direction of those charges. Okay, so this would represent the angle between the velocity and the field. Now, this also brings us to our third right-hand rule. So we had the curl rule, we had the flat wire rule, and now I like to call this one the flat charge rule. Now basically nothing really changes in this case except for the fact that instead of the current being your thumb, it's now the velocity as your thumb. Your fingers still represent the field and your palm still represents a force. However, there is one more little tricky part to this. This is the force on a positive charge. Okay, so I've drawn a little arrow here that says the direction of the force on a negative charge would be opposite. So you can think of the top of your hand as the direction the negative charge would go. Okay, and your palm is the direction a positive charge would go. And again, this takes a lot of practice, okay? So if it seems confusing at first, we're going to have to go through a few examples for it to make more sense, okay? Now, other thing to remember, basically that if the charge is parallel to the field, then the force acting on it is absolutely zero. Okay. Now, what's kind of fun to talk about here with a charge moving in a field is that there's a very big orbital connection. Okay, I'm going to pull this up a little bit. Okay, so the path of a particle in a plane perpendicular to a magnetic field. Now, what I mean by that is, all right, well, let's just think about this for a second. If I use a flat hand rule, my thumb, okay, and the field, okay, are perpendicular, and my thumb and the angle here with my palm, those are perpendicular. Well, if my thumb is a velocity and my palm is a force, those are perpendicular to each other. The only other time we've really seen that too much is in this case when something orbiting around the planet. It has a velocity that is perpendicular to its force. Well, this charge has the same situation. It's got a velocity perpendicular to a force. Okay. Therefore, if we said that the force, the electrical force, the magnetic force is equal to QVB, and its gravitational or centripetal force is mv squared over r, then we can set those things equal to each other. And we can reduce down, radius is mv over qb, or the magnetic field would be equal to mv over qr. This would be something where maybe they tell us the actual radius of orbit of the charge as it's moving through something, and actually ask you to find the magnetic field. This is a pretty specific situation, but it's kind of fun to think about here. What I've drawn down here is a magnetic field into the page. So anywhere where there's an X, that means the field is in. So my fingers, in this case, would be going into the paper. Okay, I'm going to lift this up a little bit so you can maybe see it better. My fingers are down into the paper. Okay, now if this is a positive charge moving to the left, my thumb is going to be the direction the field is down. Okay, which means my palm is actually facing in towards me, this direction, towards me, which means that positive charge that's going through that field is experiencing a force down. Well, if it does that, if it's got a velocity this way and it experiences a force down, it's going to curl. It's going to follow a round path. But then by the time it gets back here, well, now its velocity is down, so it's going to feel a force this way. Well, that's going to make it, again, curve along a path. And eventually, it's kind of hard, maybe I'll get this back down here. You see the little dashed line that I made? Eventually, it just makes an orbit around and around and around in that field. So you can actually get a charge to just orbit in a magnetic field. Now, I'm going to pose a question to you, and I'm not going to answer it until we come back and talk about it in class. But how would this picture be different if it was an electron instead of a proton or a positive charge? Okay, so we've all got through all of our different right-hand rules now. Keep in mind that one of them is a curl rule for the direction of the magnetic force around a wire. Okay, we've got a flat wire rule talking about the current through a wire. Okay, and now we've got a flat charge rule talking about a charge moving through a magnetic field. Okay, it's going to be a little tough to keep them all straight, but we'll get there.